Hey everybody, this is our lesson on states of matter and phase changes. So by the end of this lesson, you should be able to explain the phases of matter and the physical changes that matter will undergo. So first, let's go over just quickly our states of matter. So materials that we look at are going to be classified as solids, liquids, or gases. Sometimes we'll look at plasma, but that's like higher level sciences. And this is based on whether their shapes and volumes are definite or variable. So I like to use definite or indefinite because then they sound comparable. So shape and volume are clues to how your particles within the material are arranged. Are they arranged loosely? Are they compact? Are they restricted movement? Things like that. So for a solid, this is the state of matter where you have a definite shape and a definite volume. So what that means is a solid that you have, whatever it is, you can change the container that it's in. And it will still only take up the same amount of space. So it will only have a definite volume, and its shape will not change in that state. So definite here again means that the shape and volume doesn't change when moved from one container to another. A liquid has a definite volume but an indefinite shape. So here, if you have a 20-ounce bottle of water, but then you pour that water into a cup, you still have 20 ounces, but it's no longer going to be shaped like the bottle that it was in originally. It's now going to take the shape of the cup. So that's why it's an indefinite shape. So liquids always have the same shape as the container that they are being poured into. Or, the container that they're in at the time. And then you have gases, and they have indefinite shape and volume, so they can change their shape and volume based on the containers that they are put in. There we go. All right, so now let's talk about kinetic energy of gases, because this kind of explains why they're indefinite shape and volume. So kinetic energy is the energy of an object due to its motion. So this is motion energy. And kinetic theory states that all particles of matter are in constant, and I'm going to expand on this, constant random motion. So these particles are always moving. As you get into more indefinite states, so gases, that's when it gets more random. It's not very random with solids because they are very restricted, but they're still always moving. So let's talk about kinetic theory of gases, because this is the most important one to understand. So first we've got that the constant motion of particles in a gas allows them to fill the container of any shape and any size. So you could say that all the gas particles in a classroom can then be compacted down to fit into, like an Amazon box. And that's all due to the constant motion and the space between your particles. There are three main points to the kinetic theory of gases. So the first one is that particles of gas are always in constant random motion. That's the biggest one to understand. The motion of one particle is unaffected by the motion of other particles unless they collide. So this states that they don't interact with each other. They move independently of each other unless they collide. When they collide, then that could change the course that the particles were originally on. And forces of attraction among these particles can be ignored under ordinary conditions. So they're negligible. They're not going to change, again, the trajectory of these particles. So let's talk about behavior of matter, and we're going to start with gases. So gases, there are forces of attraction among particles in all matter, but they are a little bit more negligible with gases. So they're normally far enough apart and moving fast enough that these attractions can be ignored because they're too weak. So now let's talk a little bit about liquids. So the particles in a liquid are more closely packed together than they were in a gas, so they do have some attractions occurring. And we look at liquids and solids are called condensed states of matter because they have definite volumes. So these particles can flow over each other, but they're not restricted to their original position. When you look at these particles, there is a type of like tug of war between them, between the constant motion and the attractions. So the stronger the attractions, the less random motion those particles will have, and vice versa. A liquid, we know, will take the shape of the container it's in because the particles in that liquid can flow to new locations, and that's all due to the attractions and that motion. And then the volume of the liquid is constant because the forces of attraction will keep those particles close together so that they do have that condensed state of matter. So now let's talk about behavior of solids. So these particles are in a fixed location and the volume doesn't change. So this has the most restricted movement. Since they are fixed, all the particles can do, they are still moving, but their movement is limited to just vibrating in place. So they can't flow, they can't just move freely, they just vibrate in place. Got some of my gifts here. So now let's move on to phase changes. So we're going between these states of matter now. So this is defined as the reversible physical change that occurs when a substance goes from one state of matter to another. And our four basic phases are melting, freezing, vaporization, and condensation. You may have also heard of sublimation and deposition in other classes, but these are the four we're really going to focus on. All of your energy, your phase changes share a certain characteristic related to energy and temperature. So as we increase temperature, we'll get to a point where we start the phase changes and then we switch to energy changing. So the temperature of a substance, this is very important, does not change during a phase change. All of the energy that's put in is used to breaking those attractions or overcoming those attractions to go from one state to another. So once a phase change is complete, though, then the temperature can start to increase or decrease again. So we only change temperature in one state, so solid, liquid, or gas. But when you're going between states, no temperature change. Energy is either absorbed or released during a phase change. If it's an endothermic change, that means think into. So energy is going into the system. So it's being absorbed from its surrounding. And this is when we are overcoming attractions. So melting, going from solid to liquid to a more mobile phase. And then going from liquid to gas, vaporization is another more mobile phase. And then you can hear the term exothermic, think exit. So it's leaving the system. Energy is being released to the surroundings. So this is like going to more condensed states of matter. So gas to liquid, condensing, we're losing energy. Liquid to solid, freezing, losing energy. Yeah, I did not put gifts in this one. I'm sorry, guys. So the arrangement of your molecules in ice, as an example, becomes less orderly as water melts and more orderly as it freezes. So ice to liquid water becomes a little less structured because now they're able to flow around. But the opposite happens when liquid water freezes into ice. The phase change in which a substance changes from liquid to gas is vaporization. So we want to know that term. And there is a difference between vaporization and evaporation. So evaporation will take place at the surface of a liquid, that occurs at temperatures below the boiling point. So I like to think of like puddles outside. Okay, so puddles never get hot enough to boil, right? We don't see bubbles coming out of them, but over time you will see that those puddles will disappear. That's because the water is evaporating at temperatures lower than the boiling point. Vaporization is at the boiling point. So when evaporation takes place in a container, the pressure caused by the collisions of the vapor with the walls build vapor pressure. Best way to explain that is the pressure of a gas above a liquid. And then condensation, we know, is gas to liquid. So this is called a heating curve. And I know it's called a curve, but it's very straight line. Looks like stairs. This is very good to see and know the parts. So make sure you make a little note of these in your notes. So where we have freezing and melting, this is what we call heat of fusion. And that is more for melting. Okay, so we're looking at the red arrow here. And this is when energy is being absorbed, but the temperature is not changing to go from solid to liquid. And then up top where it's vaporization, it's called heat of vaporization. Again, energy is being absorbed, but temperature isn't changing. And then this is called a phase diagram. So this one also shows you the separation of each state. It shows you where the phase changes occur. And then we have two big points to know here. So the first one is the critical point, and this is the temperature at which the distinction between liquid and gas can no longer be made. So after this point, everything is gas. And then we also have the triple point, and this is where all three phases coexist at one time. So solid, liquid, and gas all exist at that specific temperature and pressure. So now, sorry, that was a little bit longer than usual, but you should be able to distinguish between your phases and then interpret